Good morning, everyone. I'm Jeremiah Fourie, Product Owner for Cogniflight Cloud. Welcome back to our presentation. So in the previous assignment, we presented our requirements for Cogniflight Cloud, a system to monitor pilot fatigue in real time. Today, we're showing you the database architecture we designed to support it. And yes, before you ask, we did spend way too much time debating MongoDB versus SQL. The answer, both, because apparently aviation systems don't believe in keeping things simple. Here's the fun part. We're dealing with 21 different sensors from multiple aircraft streaming data continuously. Heart rates, eye movements, G-forces. It's like Fitbit met flight simulator and had a very data-intensive baby. All this needs to be captured, stored, and analyzed faster than you can say normalization. Our solution. We're running a two database setup that's basically organized chaos. MongoDB handles the civilized data, pilot profiles, flight records, the stuff that changes maybe once a day if you're lucky. InfluxDB. That's handling sensor data coming in so fast we genuinely questioned our life choices. 21 different sensors from multiple aircraft, all screaming data at us simultaneously. Heart rates, microsleeps, G-forces. It's like trying to take notes during an auctioneer speed reading competition. MongoDB is sitting there all calm. Oh yes, pilot Karen has a valid license. How delightful. Meanwhile, InfluxDB is having an existential crisis. Another 1,000 data points. Wait, another 1,000. The beautiful part, it actually works. Turns out you can solve problems by throwing two completely different databases at them and hoping for the best. Today, my caffeinated team will walk you through the database design. Fair warning, there will be technical jargon, there will be complex diagrams, but there will also be a solid database design that meets all the requirements we were given. So buckle up. Susan, hit us with those business rules.
Thanks, Jeremiah. So the key business rules for our cloud platform ensure that Cogniflight Cloud adheres to strict aviation safety and data management requirements. These govern how telemetry data is captured, processed, and accessed. Let's have each one business rules that will guide us. So number one is user authentication. This requires each user to have a unique email address and role. The three roles on our system are pilot, air traffic controller, and system administrator. Rule 2 is pilot certification. Each pilot registered on the system should have and maintain valid certification, and they have to provide their license number. Rule 3 is edge node registration. Each aircraft or edge node must provide their tail number as identification on the system before their telemetry data is captured. Flight session integrity. Each flight must be linked to one pilot and one edge node, and flight details like start time and duration must be specified. Rule 5 is telemetry data continuity. Real-time, time-stamped telemetry data must be linked to active flights for real-time fatigue analysis and monitoring. Number 6, alerts generation. So fusion scores exceeding predefined thresholds must automatically generate fatigue alerts. Rule number 7 is session management. For security compliance, user sessions must be tracked with expiration timestamps. API security. Edge nodes must be authenticated through API keys before transmitting telemetry data. And file storage, user profile images must be stored securely using GridFS. And number 10 is role-based access. User roles determine data access permissions. System admins generate access tokens and can edit user profiles, while pilots have access to their own data. Air traffic controllers have access to multiple pilots' fatigue data. Let's look at the normalization analysis next. Our database uses MongoDB's document-based architecture, which is different to relational database architecture, but normalization is still required and will be applied as follows. For the users collection, we will have a denormalized embedded documents approach. This means that pilot info is embedded in user documents to improve query performance, as this avoids joins. Sessions will be normalized until third normal form to ensure it is a separate collection. Flights will also be in the third normal form and will reference edge nodes and users via unique object IDs to ensure referential integrity. The edge nodes collection will be in the second normal form with plane info embedded as an atomic unit. Alerts will be in the third normal form with pilot references maintained separately for historic alert analysis. API keys will be normalized until the third normal form and stored as a separate collection. The benefits of normalization for our database will thus include the elimination of data redundancy, data integrity, flexibility, and performance optimization. Over to you, Brian.
Yeah. Thank you, Susan. So first, I would like to show off our ERD. This is for MongoDB, and I'll walk us through a scenario here. So let's say a person signs up, right? So two things happen in sequence. First, we create that user record, and a sessions record gets created alongside of it. And that session references that user, and it gets passed as a cookie. That's how we know that that person is logged in. This is that person. And then let's say they start uploading images, right? This is a pilot. He's starting to set up his account, so he uploads a few images. It's used to generate a few embeddings that's stored separately. And he also identifies one of them as a profile image, and then that gets referenced in his user's record. And then he navigates to the settings, adds his own pilot info, stuff like his license number, his certification expiry, how much he's flown, and that gets added to his user's record right here. And then say, this guy's actually going to have to fly something. So let's say an admin decides to go ahead and creates an edge node on the server, and the edge node's obviously also going to need an API key. The API key references that edge node, and it's also used by the MQTT authentication and by our API. And that API key entity also works for non-edge nodes. It can work for third-party integration. That's what would happen if we don't have that reference. And as you can see, we also have secure hash storage for that API key, and it has a string representation. And that's how we know that this is completely secure. And as that edge node sits there doing its thing, it notices, hey, we're about to take off, so it creates a flight. It identifies the pilot with facial recognition. It says like, hey, here's my edge ID. This is the pilot that we're going to be flying with, and we're starting right now. And then that flight record gets made, and the edge node starts streaming data like crazy, sending everything. Show on the next slide everything that it's going to be sending. And as the fusion score gets high, the backend detects and makes that alert. And so here we have that demonstration as well. So the telemetry data that the edge node is going to send, we have it tagged with these three fields. First, of course, the flight and the pilot, just for ease of use, and the aircraft, which is associated with the edge ID, which is why it sends its edge ID as well. And you can see on the right side here, we have a little flowchart of what exactly happens. First, that flight gets made, then all of that InfluxDB telemetry data gets sent, and as it gets sent, it triggers actions on the Python ML engine that decides let's make an alert, and this is our interpretation of why this guy is suddenly so tired, or why there's a problem going on here, and that gets added to the alert collection, which also references the pilot, so the pilot can later go back and he can say like, oh yeah, sorry, I was really tired, had a bit of a rough weekend, we were all over the place for some reason. And yeah, here you can see all of the fields that we've got here as well. We've got the most important ones are the core metrics. These are the intelligent fields generated by the edge node, specifically the stress index and the fusion score. The fusion score is trusted as a pointwise calculation of the person's fatigue at that specific point in time. And then we have all the heart rate data that comes from the heart rate sensor, the environmental data that comes from all kinds of sensors that are attached to the machine. And then we have the eye tracking, which is going to be from the camera, and we have the motion sensors as well. And then on the next slide, you'll find that we have different principles, sorry, that's the next one. Here we have the relationship. So when you delete something that has a reference, if you do it, you're going to cause problems. You're going to cause orphans. If you have delete the reference while the thing that has the reference is still around. So we have the specific procedures that we're going to follow. So here for the users to sessions, you'll see cascade delete. That one's obvious because the sessions, that's just to say that users log in. So that has to die. And for most of these other stuff, you want to restrict delete because there's a lot of important data that we want to keep track of until we explicitly want to delete it. So it'll be demanded for stuff like all the flights that user has made, the alerts, and all of the telemetry data that you would ask on the front end first, like, are you sure? Like, if you delete this thing, everything's going to go. And this is what the restrict delete is for. And the cascade delete is just a different handling of it as well. In that case, we just also have a little warning like, hey, you're about to delete everything. And then here on the next slide, we have our principle. We have 3 principles that we have identified. First, your entity integrity. That means that specific entity is intact within the context of its collection. So you have the primary key. Everything has to have a unique primary key. And you have the unique constraints. You're an example for our user. Emails have to be unique, and many of the fields are required, especially things like, we actually have to have a password for the guy to log in and everything. And then for the referential integrity, that's what makes the ERD thing possible. That's so that the different object IDs do actually reference specific stuff, and that's also why we had to have the restrict delete and the cascade delete stuff from the previous slide. And the domain integrity, that refers to specific field stuff that limits what can be put into that field to what makes sense, right? Like the role can only be one of those 3 things. The fusion scores can only be between 0 and 1. And these are obviously all enforced by validation schemas that are created with collections upfront. And for that, I will pass over to Jaden so that he can explain that part of our code base.
Thank you, Brian. So yes, for everyone watching this video, I'm going to be doing the MongoDB schema. So for all MongoDB schema for Cogniflight Cloud is designed to be flexible, but with strong guardrails that protect data quality. We start by initializing the database using a JSON validation schema. This ensures every insert follows the right structure. So no missing fields, no wrong data types, and no bad values slipping in. The user collection holds core identity and login info. For example, name, email, and password and role. Emails are unique, passwords are always hashed, and roles are limited to the pilot, ATC or sysadmin. For pilots, we add extra details like license number, expiry date, and flight hours, plus profile photos stored in a separate in CRUD FS. Flights link pilots to their edge devices. We start times in UTC and precise durations in milliseconds, perfect for analytics like flight length and for utilization. Alerts capture fatigue data, a fusion score between 0 and 1, an interpretation and optional pilot notes for context. This way, alerts are both machine readable and human actionable. Across all collections, validation rules keep data consistent and smart indexes. On things like user emails, flight times, and pilot alerts, make queries and dashboards fast and efficient. In short, our schema gives us the best of both worlds. MongoDB's flexibility, but with the readability and real-time use analytics needed for operations.
Good day, ladies and gentlemen. My name is Jeremy here, and in this portion of the presentation, I'll be making use of sample data that will be created within the DB database. I'm going to start off with the user database. In the user collection, we store information of the users that will be implementing this program. It could stem from the pilot all the way to the system admin and those who use the application regularly. So within the users collection, we have 3 document examples that I'll be explaining to you just quick, starting off with the first document, which will then represent the pilot called Captain John Smith, his email, his phone number, his password, which is then hashed for security protection, as well as his role as a pilot. And within that role as a pilot, we pretty much have extra information on that role, such as the license number, expiration of his certificate, as well as the amount of flight hours he has taken in his entire career, which is 5,420. The next document, we pretty much have a name called Sarah Johnson, which is the user of the program, an email, phone number, password, as well as an ATC. The last document in this case would be the name admin user, which will be in charge of the admin for the program itself, email, the phone number, the password, as well as the role as system admin. Now let us go to the next slide. Second off, we have the edge nodes data. Edge node in this case is the physical aspect of this project, such as the plane itself. Pretty much be making use of data relating to the information that's going to be stored about the plane, such as its tail number, its manufacturer, its model, as well as the year it was created. In this case, within the first document, we pretty much have the tail number of 12345, the manufacturer being Kessner, model being 172, and the year that was being created being 2020. It's pretty much the same thing for the next document, so go over to the next slide. Now we have the flight data. Within the flight data, we will pretty much have a record that will link the pilot to his or her particular plane. Pretty much declare two variables for the pilot and the edge to pretty much get the pilot and the plane from their respective IDs within their respective collections. And within the flight collection, we have two documents. The first document having the information for the edge and the pilot, which is then obviously the one that you just described above. The start being start of the flight. So again, we have the date as well as the time, and the duration implying how long it will take to go from point B measured in milliseconds. And once you convert that over that value of 7.2 over to hours, it will give us a value of 2 hours. The second document is pretty much the same gist. However, the difference obviously in this case would be the date and the duration, the date being different and the time being different, and the duration being slightly shorter, with a total amount of 1 point in the year. Let's go to the next slide. Finally, we have the alert data, which in this case also be sent from the edge node. However, the difference between the edge node collection and the alert data is that within the edge node is just information about the plane, and the alert data is pretty much the sensors from the plane that will be sent from the hardware side all the way to the cloud side. And yeah, within the alert collections, we have two documents, pretty much identifying the pilot ID, which is obviously there's Captain Smith, the timestamp in which the alert was sent, which is the date and the time. The fusion score being above 7 implies that it is a critical emergency, with the interpretation being from that of the Python machine learning algorithm, which will pretty much give a liquid message based on the fusion score, and the user explanation being that from the pilot or someone on the planes explaining why they are the way they are based on fusion score. And within the second document is also pretty much the same gist, alongside the pilot the timestamp, which is then new to give us a different perspective. The fusion score being way higher than the first, implying that it is a very critical alert that will have to be sent within seconds to the cloud and the database, as well as the user explanation saying that, hey, this extended flight in the challenging weather conditions. This is over to Jason.
All right. So as you can see, this is clearly a MongoDB-based aviation management system designed to handle user accounts, flight records, and operational data for both pilots and general users. The system emphasizes data integrity, regulatory compliance, and operational efficiency. So now, with the CRUD Operations, the user creation builds comprehensive user profiles with role-based architecture, distinguishing between regular users and certified pilots. This uses conditional logic to store pilot credentials when applicable and automatically timestamp all registration for audit trails. The flight creation generates permanent flight records with relational references connecting flights to routes and pilots through the object ID conversions. It also stores timing data with high precision using number.long formats to meet regulatory and billing requirements. Now, with the read operations, we have authentication, which performs fast email-based user lookups for secure system access. The flight history retrieves complete pilot flight histories with chronological sorting from the newest first to support scheduling and performance monitoring. The alert management fetches recent pilot notifications with intelligent pagination, which defaults to 10 alerts to prevent information overload, whilst ensuring timely communication. Data integration is done through the performance of complex aggregation queries that combine flight records with pilot profile information, creating comprehensive reports for compliance and oversight. The update operations are done through profile management, which enables selective field updates for user profiles using conditional logic to modify only selected fields while preserving unchanged data. The flight corrections provide targeted duration updates for flight records using high precision storage to maintain accuracy for regulatory and billing purposes. Now with the delete operations, you have the user deletion, which implements two-phase comprehensive cleanup that removes associated sessions and temporary data before deleting the main user record, preventing orphan data and security vulnerabilities, as Brian mentioned earlier. Flight deletions offer controlled removal of flight records, primarily for erroneous or duplicate entries, while maintaining the permanent nature of most flight data. So here are the key system characteristics. So this relational structure uses object ID references to maintain relationships between users, flights, and routes. Performance optimization is done through pagination, selective updates, and efficient data structures. It is also designed for aviation environments requiring speed, reliability, and regulatory compliance, which places an emphasis on safety. Comprehensive cleanup procedures and cascading deletion prevent data corruption, and automatic timestamping and detailed operation feedback support administrative oversight by allowing for audit capabilities. I now go and pass on to
Brian
for this next section.
Thank you, Jason. So these queries here are the type of thing that you would throw onto a dashboard or you would pull as a PDF, have a report. These are the things that you could give to an admin to help with managing all of these pilots and all the flights and all of the routes that they're going. On the left, we have our fatigue analytics, which refers to, for this pilot, we have here what's the average fusion score and like the spike according to the alerts that they have on a specific day and how many alerts happened on this day. So you could use this graph that you could plot from this query to identify different pilots, to identify problems, to find pilots that are struggling and ask are they in good health? Is everything going well? Or is this maybe associated with a specific aircraft or an edge node? What's causing this problem that this pilot is always so tired while they were flying? And then on the right side here, we have our fleet utilization. And this is specifically probably useful for maintenance schedules and all those kinds of things, because it calculates the amount of flights for every single aircraft, how much you've flown with it, like what's the average duration of a flight that you go with it. And it's obviously also sorted in reverse, so you know which aircraft you're using the most. So that also means you have to pay more attention to the aircraft that you see up first on the report. And then I will want to give over to Janku to show the power of our InfluxDB.
Great, thank you, Brian. So moving on from our MongoDB operational data, let's explore how we handle the high-frequency telemetry streams that are the heart of our fatigue monitoring system. So we chose InfluxDB as our time series database because aviation telemetry generates thousands of data points per minute. Traditional relational databases simply can't handle this volume efficiently. So our schema is built around a single measurement called flight telemetry with 3 key tags: flight ID to link back to our MongoDB flight records, pilot ID for direct pilot association, and aircraft identifier for fleet-wide analysis. So here's a quick overview of our telemetry fields architecture. What makes our implementation powerful is the wide range of sensor data that we capture. As Jeremiah mentioned, we have 21 distinct fields which we organized into 5 categories. First, our core metrics, which is the stress index and the fusion score. These values are calculated by our machine learning engine to indicate the fatigue levels. Then we have heart rate, which gives us 4 key indicators. We have the baseline heart rate, the deviation from the normal patterns, RMSSD, which measures the heart rate variability, and then the overall trends. Environmental factors such as temperature, humidity, altitude, which can help us understand external stresses affecting the pilot's performance. Then eye tracking is of course very crucial for fatigue detection. We monitor average eye aspect ratio or EAR during the duration of the eye closures, the micro sleep events, and then the blink patterns. Finally, we have motion sensors, which can capture the movements of the aircraft through a six-axis acceleration and rotation data, plus the climb rate. This tells us about how the flight complexity and workload can work in on the pilot. Now, how do we use all this data? So the magic happens with our machine learning engine, which queries this time series data for real-time fatigue analysis. The code you see demonstrates how we pull telemetry data for a specific pilot within a time range. Notice how we use InfluxDB's pivot function to transform the data into a format our machine learning algorithms can process. Each data point is a snapshot of the pilot's physiological and environmental state at that moment of time. The data flows directly into our fatigue detection algorithms, which then generate alerts that are stored back in our MongoDB alerts collection, completing the circle between our two database systems. The hybrid architecture that separates the concerns works perfectly. MongoDB handles the operational metadata, while InfluxDB manages high-frequency telemetry. When machine learning algorithms detect fatigue detection patterns, they generate alerts linking back to the flight records for complete audit trails. This enables real-time fatigue monitoring, predictive analysis, regulatory compliance reporting, and fleet-wide scalability, moving aviation safety from reactive to predictive analytics. I'll then hand over to Jeremiah to close for us.
Thank you, Janku. Processing 21 telemetry fields coming from multiple aircraft in real time is no joke. So let's wrap this up. As you can see on this slide, we basically engineered a database equivalent of a Swiss Army knife, except it's specifically designed for aviation data and won't fit in your pocket. 3 things we're particularly proud of. First, our hybrid architecture. MongoDB and InfluxDB living together in harmony. It's like we've solved world peace. Database world peace. We can handle everything from boring user profiles to exciting microsecond telemetry data without breaking a sweat, or at least without a database breaking a sweat. We definitely did. Second, security that would make a paranoid system admin smile. Role-based access, API keys, session management. Basically, pilots can't accidentally see each other's embarrassing fatigue scores. And that's what really matters, privacy and safety. Third, performance that actually performs. 21 telemetry fields processed in real time. With indexing so good, it makes our queries faster than my roommate claiming the last slice of pizza. We're talking millisecond responses for months of data. Now that we have played it safe with a simpler, now we could have played it safe with a simpler design, but we decided to challenge ourselves with something complex and meaningful. When this system detects a fusion score above 0.7, it's not just triggering an alert, it's potentially preventing the kind of incident that makes the evening news. This team has put together a database architecture that's scalable, secure, and ready for the cloud. We've normalized it where it makes sense, denormalized it where it doesn't, and documented everything for the poor soul who has to implement this. Which is us. We are that poor soul. So there you have it, Cogniflight Cloud's database design. It's not operational yet, but when it is, it'll be processing telemetry data faster than you can say third normal form. Thank you for your attention, your patience with our aviation puns, and your tolerance of our caffeine-fueled enthusiasm. We're ready for your questions, technical, theoretical, or just why aviation. And have a lucky day.